Yes, next week, Wednesday. Yep. Okay. All right, so as far as I know, what's up?
Is this still labs? Yes, lab, no class.
Well, I mean, instead of a lecture, there'll be an exam. But yeah, there still is a lab, unfortunately. So next week's lab 6, I think. And we're skipping 7, and we're doing 8 last, I believe. Yeah, I have to look at the schedule. But we do have a lab normally.
Yeah, it's stoichiometry rockets, right?
Yeah. That's near the end, yeah. But we haven't even done any of that, so that's later, yeah. Okay, so I believe this is the last thing we talked about, was looking at density with the ideal gas law. And again, that's provided. You don't have to worry about memorizing this. I don't even have the equation listed, but the equation is pressure times molar mass is equal to density RT. But again, you'll get that on the exam. You'll get that on the exam, because we're not going to have a quiz next week. And you can use here, let me write that down just so it's there. Pressure molar mass is equal to density RT. And so as I had that the right way, right? The density goes up, the pressure goes up as the molar mass goes up. Yeah. Okay, I think this works. Anyway, so the idea here is if you're looking at a balloon, if the pressure and the temperature are the same, a heavier balloon, or heavier gas, will have a higher density, and so that's why methane will float, since it's lighter than air, so it'll be less dense. And a balloon of carbon dioxide will sink because it's heavier than air. The molar mass is higher, and so we'll have a higher density. Okay, this is the one thing, and we saw the video. I think that's the last thing we did. So this is the thing that I wanted to get to. We didn't have time last time. So what happens when you have mixtures of gases? How do you calculate pressure and volume and all that, number of moles? Well, the simple answer is, since ideal gases, it doesn't really matter what their identity is. A mixture of gases is going to behave the same whether it's a pure gas or a mixture. But what if we want to know, well, what if we want to talk about the individual gases in the mixture? So this is where it gets a little weird. We can talk about their partial pressures. So if I have a mixture of gases in a container, each gas in the container can be assigned its own individual pressure. That's what we call a partial pressure. And if we add up those partial pressures, we will end up with the total pressure, the pressure of all the gases together. You'll see how this works. It's all math-based. PV equals nRT works the same way. So with PV equals nRT, you can treat all the gases as the same. And so if you want to calculate the pressure of all the gases inside a container, all of them together, that's the total pressure, then the number of moles will be all the moles of gas. So the sum of all the different moles of gas. But with partial pressures, let's say you're only interested in gas A. There's gas A, gas B, gas C, whatever is mixed together. Well, all I would need to do is just plug in the moles of A, and that's it. So it's still the same equation. You're just kind of limiting which gases you're talking about. And you can do it with basically talking about all the moles or just a specific number, like for the gas you're talking about. That's how partial pressures works. And here's a visual of what you might see. Here's a container at 5 liters at 20 degrees C, and we've loaded it with half a mole of hydrogen gas. And if you calculate what the pressure would be, it's going to be 2.4 atmospheres. But let's say I take the same size container at the same temperature, and instead I put 1.25 moles of helium in it, different gas, more moles of it, Well, if I calculate the pressure, it's going to be 6 atmospheres. If I put those two gases together into the same container, the total pressure is going to be literally the sum of the two individual pressures. So 22.4 and 6 is going to be 8.4 atmospheres. But individually, inside this container, the partial pressure of the helium gas, the red one, is still 6 atmospheres. The partial pressure of the blue one, the hydrogen gas, is still 2.4 atmospheres. Now, the way I got total pressure was to just add those two partial pressures together. I still could have used PV equals nRT. I could say, well, the volume is 5 liters. The temperature is 293 Kelvin. And the number of moles is, well, there's half a mole of this, and there's 1.25 moles of this. There's 1.75 moles of gas total. And plug it all together, so there it is, and plug that all into PV equals nRT, and I will get P total as 8.4 atmospheres. So what this is doing is it's letting us solve these numbers from various routes, okay? So sometimes you'll have a couple choices. Sometimes you'll be limited. You'll have to do it this way. And that's what's going to make these problems a little bit difficult. These are, word problems, yeah.
So PM equals DRT is for density?
So this M is molar. So this is a derivation of PV equals nRT.
Yeah, for molarity, or for...
Yeah, and so we managed to insert density in there. And as a consequence, suddenly the identity of the gas matters. The molar mass you need to plug in.
Oh, okay, cool.
So that's molar mass. And that's separate from what we're talking about now.
Yep, just wanted to make sure.
Okay. All right, so...
Wait, sorry, could you go back?
yeah. By the way, this math symbol, this is capital sigma, and that's math for sum of all of the individual pressures.
It's like in every class.
Yeah, but just in case somebody hasn't seen it, but hopefully you've all seen it. So now a few extra concepts. There's this thing called mole fraction, which I think you know fundamentally. This is just, we're introducing it formally. Mole fraction is a fraction amount of like, so if I have a mixture of gases, what is the fraction of the gas that is a certain gas? So if I'm interested in the hydrogen gas, what is the mole fraction of hydrogen? Well, I would plug in the moles of hydrogen, 0.5, and I would divide it by the total number of moles of the gas mixture, so 1.75 moles. And it'll be some fraction. It's like percentage without the times 100%. That's what a fraction is. FYI, the mole fraction symbol that you see there, well, it looks like a capital X. It is technically the chi symbol, that capital Greek chi symbol. Don't worry about it, but you'll see it written formally like this, and that's
called chi.
I think it's chi, yeah. All right. But that's mole fraction, and you'll see subscripts, and the subscripts will say, oh, the mole fraction of gas A. So why do we care about mole fraction? What is it? How is it going to help us in this case? Well, it turns out that if you multiply the total pressure of a gas by the mole fraction of an individual gas, you will get the partial pressure of that gas. So basically, the partial pressure is proportional to the mole fraction. That's basically what we're saying here. So if you can figure out the mole fraction, so I don't know if there's going to be an example shown, but let's do one real quick. The mole fraction of hydrogen is 0.5 moles divided by the total moles, 1.75. So the mole fraction is let me label this. The mole fraction of hydrogen is 0.5 divided by 1.75 is 0.2857. That's not the right sig figs, but it's fine. So that's the mole fraction. The total pressure is 8.4 atmospheres. So if I multiply the total pressure by the mole fraction of hydrogen, I will get the partial pressure of hydrogen. And it should be, what is it, 2.4. And it is. So this times 8.4 is exactly 2.4. Yes?
Where did you get the 1.75?
Okay. So the idea here is,
I
yeah.
didn't see that. I was looking at the first one. Sorry.
So taking those two gases, we put them together in the container. There's still 0.5 moles of hydrogen.
Yeah.
Total, there's 1.75.
Okay,
Yes.
I just didn't see that. I just
No
didn't
problem.
see
Yeah,
that.
no problem. Yeah.
So if we're given like, instead of in moles, if we were given like the volume of the gases, say like in liters,
Uh-huh.
do we have to convert them to moles to find mole fraction?
So, if you're given just this, and you're given a volume and a temperature, and that's it, you can't do it because you need a partial pressure to get the moles of a particular gas. So for any gas, you need at least 3 of those variables to understand the state of the gas, right? So there's pressure, volume, temperature, and moles. Those are the 4 variables you need to fully describe a gas. If you're missing one, that's okay. You can calculate the 4th using P equals nRT. But what I'm showing you here is the various ways these are all interrelated, okay? So there's going to be cases where you're missing one thing and you need to calculate it. So you could take the mole fraction route. So let's say you have the total pressure and you want to find the partial pressure. Well, you could take the mole fraction route and use that to calculate partial pressure. Or you could use PV equals nRT and calculate the partial pressure. I could plug in temperature, the number of moles, the volume, R, and find partial pressure that way. So there's going to be various ways to do it. Sometimes you'll have to do it one way or the other. Maybe you don't know the volume. Maybe you don't, so you have to do it this way. Is that going to make sense? We need to practice some problems. That way you'll understand what all of these are tools now. Think of them as tools in your toolbox, how we're going to use them. So here's a question. I've got this container, and it's a very tiny container with a very small number of gas particles. But that's okay. Remember, what is moles? Moles is a way to count particles, a large number of them, but it's just a way to count particles. So if I count literal particles, it's the same idea. So here is this. We're telling you is the total pressure is 600 millimeters of mercury. What is the partial pressure of each of those gas particles? So they have the red gas, we have the green gas, and we have the yellow gas. Well, I don't have temperature, I don't have a volume, so I'm not going to use PV equals nRT. Let's use the mole fraction idea. Because if I can find the mole fraction of the red gas and multiply it by the total pressure, which I've got, that will give me the partial pressure of the red gas. So how do we get mole fraction of the red gas? Count red versus the total. Yeah, so I've got 1, 2, 3, 4, 5, 6 red atoms out of 12 total. So the mole fraction is 0.5. Half of this gas is red. So now I've got 0.5 for my mole fraction. The total pressure is 600 millimeters of mercury. And so the partial pressure of the red gas, notice that the units don't change. This mole fraction is unitless, so it's 300 millimeters of mercury. All right, and we keep going. We do the same thing for the green one. The partial pressure of the green one, well, let's actually calculate the mole fraction first. Mole fraction of the green gas, there's 4 atoms of green gas out of 12 total. That's a third. And now we do the partial pressure of the green gas is going to be a third times the total pressure, 600 millimeters of mercury. And that is 200 millimeters of mercury. What's the partial pressure of the yellow gas? You could do these calculations for the yellow gas if you like. There's an easier way. So what are the all the
It's
partial pressures
100.
add up to.
So P total is going to be the sum of all the partial pressures. So times one partial pressure, you have to subtract the other partial pressures from the total pressure.
You did PG twice. And you went like PR for one of them? Oh no, that's that.
There's PR.
Oh, right.
Yeah, so, but what she was saying is exactly right. The sum of all of the partial pressures should add up to the total pressure.
Well, isn't the total pressure 600 and that one's 200? So
Yeah.
600 minus 200?
So it's 600 minus 200 minus
100.
300.
Oh, I did see that.
So there's 3 gases, and so the last gas is going to be 100 millimeters of mercury. And I guarantee you, if you do the mole fraction route for the yellow gas, it's going to give you 100 as well. Okay? So this is the kind of thing you're going to have to do. You're going to have to say, well, what do I know? What equations can I use? Is it a change of state, or is it just we're just calculating what's missing kind of thing? There's no state change here. All right, so we don't have to use any kind of P1, V1, P2, V2 kind of thing. There we go. Okay. Yeah, we didn't do this one yet. So let's try this one. I've got a 2-liter container. It holds 4 moles of O2 and 2.7 moles of helium. What is the partial pressure of O2? What is the partial pressure of helium? What is the total pressure? And I'll tell you, there's 2 ways to do this. We could do it in order: partial pressure of O2, partial pressure of helium, and then we can add them up and get the total pressure. Or I can add the moles together and find the total pressure first, and I can then do mole fraction times the total pressure to get the partial pressure. So there's so many, well, not so many. There's a few different ways. So let's do it, since we did mole fraction, let's do it the way they're asking us. Let's find the partial pressure. Let's use PV equals nRT. So the partial pressure of O2 is going to be the number of moles of O2 times R times T over V. So moles of O2, 4 moles. R is 0.08206. I'm not going to put units because it's a pain in the butt to write them. 293 Kelvin is the temperature. And our volume is 2 liters. So the partial pressure of O2 is, let's see, 4 times 0.08206 times 293 divided by 2, 48, I think it's just 3 sig figs. Yeah, 48.1 atmospheres. Why atmospheres? Because the units for R have atmospheres in them. So your pressure is going to end up being in atmospheres. We'll do the same thing for the helium. So we want the moles of helium, 2.7. There's R. Temperature is the same. It's in the same container. So the temperature is going to be the same. Same container, so the volume is going to be the same. And so the partial pressure of helium is 2.7 times 0.08206 times 293 divided by 2. No, I did that wrong. 32.5. I got a decimal in wrong, but I think that's it. 32.5 atmospheres. So we got our partial pressures. The total pressure, well, there's only these 2 gases. So if I add them up, I will get the total pressure. And so it's 48.1 and 32.5. No, I think I did something wrong somewhere. Hold on. Let me do this again. 0.08206 times 293. Yeah, divided by 2. 0.08206 times divided by 2. 32.5. Did I do this one right? Hold on a second. 4 times 0.086 times 293 times 2 divided by 2. Okay, I did it right. I'm just not remembering the correct answer. Oh, I edited it wrong. Okay, sorry, 80.6 atmospheres. Hopefully that's it. Okay, so that's the total pressure. Now, just in case, let's do it the other way. Let's see what we get. So let's at least calculate the pressure the other way, which was, let's use PV equals nRT. And instead of plugging in the individual moles, let's plug in the total moles. So 4 plus 2.7 is 6.7 moles. And the gas constant is 0.08206. Temperature is 298. And then the volume is 2 liters. I think there's some rounding errors probably here. Well, let's see. 6.7 times 0.08206 times 2, sorry, not 98, 293. Here's the mistake. Divided by 2. I get the same thing, 80.5. So rounding errors a little bit, but you get the same result. That's the total pressure. And then how would I get the partial pressures from this? Well, now I can do mole fraction. And then multiply mole fraction by total pressure. Yeah?
How did it make that thing quiet back there?
Oh, it's making noise again?
Yeah.
Put something heavy on it. There. It's ringing.
Really bad.
That help?
Thanks,
Okay.
yeah.
Resonance frequency.
Why are the guys on the inside and the girls on the outside of the circle?
I don't know.
That's really weird.
It's segregation.
I just noticed that you guys all do that.
Maybe you guys smell bad. I don't know.
Probably.
Maybe it's me. All right.
Their eyesight.
So, yeah, worse eyesight. I'm not going to go through all the partial pressure stuff, but again, you can calculate now what is the partial pressure of O2, and it's going to be the moles of O2 divided by the total moles, and then we can multiply this by this, and you get the partial pressure of O2. So, like I said, there's multiple ways to approach these problems now. Okay. All right, so next slide deck. That's a good reminder. And there we go. Oops. All right, so let's try this one. And so this one is a pretty gnarly problem. When you look at it from scratch, you're like, how in the world do I start that? So let's say we have 3 flasks. There we go, right down here. And this is how they originally were. Originally they were completely separated. This one has helium in it. 1 liter of it at 200 torr. This one had neon in it, 1 liter at 410 torr. This one had argon in it, 2 liters at 250 torr. So then we connect them, and let's assume that the tubing that connects these has no extra volume, negligible volume. We're not adding a lot of volume from the tubing. But let's say we connect them together and open them. And so now these are all mixed together. What is ultimately the total pressure of the gas in that system?
The sum of all the partial pressures.
Yeah, so what we're going to do is we're going to first calculate the partial pressures of each gas. And this is the magic of partial pressures. I can ignore all the gases except for one of them. Let's start with one at a time. So if we look at helium, before it was in this flask, after it was in all the flasks. That's a change of state. So what's changing in this state? So the temperature is constant. Are the number of moles of helium changing? No.
No.
So what's changing? The volume and the pressure. So the volume was 1 liter. Now what's the new volume?
Depends on what we open up in that.
All of them together.
Oh, then 4
4 liters. This and this and this together. That's the new volume. This is just a Boyle's law problem. The pressure and the volume are changing, and that's it. But we're going to apply partial pressures to this. So ignore all of the gases except for the helium, and we're going to calculate, well, what's the new pressure of helium? Okay, so for helium, P1 V1 is equal to P2 V2. That's Boyle's law. And we care about the new pressure, so let's just solve for that right now. P2 is P1 V1 over V2. Divide both sides by V2 to move it over. So the original pressure was 200 torr. The original volume was 1 liter. The new volume is the sum of all of the containers. 4 liters, yeah. And so what is the new pressure? 200 times 1 divided by 4 is 50 torr. Now, that's the new pressure of helium. That's a partial pressure because we're going to be mixed with other gases. But that is the partial pressure of helium after the containers are opened. Okay. So we just need to do the same thing for all the gases. So let's keep going. Let's do the next one, neon. And this is where you're going to have to label and separate so that you don't mix things together and you know what is what. So same formula. What is the new pressure? P1 V1 over V2.
410
410, yeah.
times 1 divided by 4.
And so the new pressure is, oh, can't do that one.
102.5.
102, thank you. Okay, and then finally we'll do argon.
I believe you.
P2, let's just, I'm not going to write it again. Let's just plug in the numbers. For argon, it's 250 torr.
Oh yeah, but this is pretty simple.
The original volume was 2 liters. The new volume is 4 liters. So the new pressure for argon is
125.
Yeah, 125. Thank you. So we've got our partial pressures for all the individual gases.
So what does it mean?
What is the total pressure after the system has been opened together? The total pressure is the sum of the partial pressures.
Yeah.
So we've got 50 and 125 is 175 plus 102 is 277.5.
I didn't realize we answered everything.
So the total pressure, I think if I did that right, 277.5 torr. So, sounds like a really complicated problem, and it is, but you boil it down to partial pressures, and then it gets super easy. It's just Boyle's law. So I will definitely admit that the difficult part of these problems is understanding how to start. So you've seen this problem now. You can hopefully do it yourself, right? Okay. Notice you can't use PV equals nRT on this. We're missing temperatures. I mean, they're telling us temperature's constant, but you can't find moles for these things because we don't know enough information. So we had to do it this way. There was no other way.
I see words. I really didn't want to do that. And then I could scan all these as formulas.
Yeah. So let's, now that we've done that, I want you guys to try one. And now we go back and do this problem here.
Is this from like the practice quiz?
This is from 31 alternate exercise number 2. So in your we skipped this problem, but you couldn't do it. Why don't you guys try this? It doesn't matter that we don't know what these gases are, and it doesn't matter if they're the same or not. Let's treat them as different gases. Let's find the partial pressures of each of these gases, and then use that to find the answer to the problem. You guys do it. Take 5 minutes or so. That should be a big hint about what's coming up in the exam.
No, it doesn't really matter though. You don't need to switch it to Tor. But in this situation, thing is the exact same. There's no actual difference to the actual.
So the
Put it in place of that.
the only unit that must be always that unit is Kelvin. Temperatures must be in Kelvin no matter what. But when you're doing
Pressure.
changes in state, as long as the pressure is the same unit before and after, it's fine. The only time
which
you
could be ATM or it could be Tor.
Yeah.
Or it could be something.
the only time you have to do a certain unit is if R is involved, the gas constant. And then you have to use the same units R has.
Okay. Cool. So then it's just.
And which page is this?
So this chapter starts at 146, I
It's
think.
on page 149.
So 149, yeah, okay.
Oh, wait, the total.
Oh yeah, that's that. Excuse me. Oh.
Which iPhone is that popular?
Yeah, it's just those two. It only matters if your hash is confirming that this is on the first one. No.
Pressure.
You did the math right, but I have no idea where you got that number.
No.
That's what my calculator is.
How would a number be divided by a lower number equal a point?
You tell me.
Oh, take one point.
This is right now.
Yep.
Okay. See, I need you, otherwise I won't be able to pass.
You just need to get a calculator.
Is anybody getting an answer?
Oh, that's
Yeah.
Close?
It's in my.
Okay, good. So, ignore sig figs here, but 226, no, that's not right. Hold on.
It's 2.8.
10 times 7, no, I did 70. That's why. 7 times 10 divided by 25, 2.8. Somehow I did something wrong. And then the that's the first tank, and the second tank's gas is going to be 10 atmospheres times 15 liters divided by the new volume, 25 liters. 10 times 15 divided by 25. 6 atmospheres. So the total pressure is going to be 8.8 atmospheres. You add, 8 TM. You add those two together. Good? Everybody golden? This is easy now, right? Now that you've seen it, you know how to do it. Okay. So whether it's 2 tanks or 5 tanks, I mean 5 would be rough, but you could do it. It's all the same. Okay. So we're going to come back to the kinetic molecular theory, which we started to look at when we talked about vapor pressure. And when we did the kinetic molecular theory, I think we just kind of hand-waved and said, well, the results gave us that Boltzmann distribution. So let's come back and let's talk about specifically what are we assuming when we talk about the kinetic molecular theory. So what is this? This is a model for describing how gas particles interact with each other. This is an ideal model, an ideal gas model. So this isn't really how they work, but it's a good way to talk about gases in general. There's going to be cases where this doesn't work. It's not appropriate, but in general this works. So first, we are assuming that these gas particles are spherical, which is not true for a lot of things, right? They're different shapes, but let's assume they're spherical. And they behave in a state of constant random motion. That's pretty fair. The particles move in straight lines until they collide with another particle or with the container walls. So boom, bounce, the kind of standard physics movement. Yes?
Why do they move in a straight line?
Well, if they're going in one direction, they will continue to go in that direction, and there's nothing that influences them to kind of veer off. And this is where IMFs come in. If there was intermolecular forces, attractions, they might veer off because they're attracted to some other gas.
That's what I was thinking about.
But, well, we didn't get to that yet. The particles exert no attractive forces on each other. So why can we make that assumption, even though we know IMFs exist? Well, in a gas, the particles are very low density. I mean, the gases are super low density, meaning there is a lot of empty space between the particles. They hardly ever get near each other. They hardly ever collide with each other. I mean, think about if you've got these tiny, tiny particles in all this empty space. It's like things flying around in space. How often do satellites hit each other? Hardly ever. I mean, of course, that's going to happen more often with a gas, but it's statistic. Like when you think about how often that occurs, it's very, very, very not very often. So if they're not getting close to each other, we can ignore the IMFs. The part where it's not as easy is what about the container walls? They'll eventually hit a container wall and bounce off. Well, we're going to assume that there's no interactions with the container wall either. Why? Why can we make that assumption? Well, what else do we know about gases? What about their energies? Are they high or low? Compared to solids and liquids, they're much higher. They've got high kinetic energy. So they're moving fast. And the idea is when they collide with something, they'll just bounce off. We can assume they don't lose too much energy when they do that. That's not exactly correct, but it's an okay assumption to make. This is the ideal gas thing. We're assuming that these particles don't take up any room. They have zero volume themselves. So if I take a bunch of gas and fill it into a 2-liter container, how much space is left in the 2-liter container? 2 liters. The gas particles don't take up any room themselves, which is not true, but we're going to assume that. This is kind of what we looked at before. The average kinetic energy of the gas particles is proportional to the temperature of the gas particles. And if you really care, I posted that link about what temperature really is and what negative Kelvin temperature could be.
Oh, is that what that was?
Yeah, it's weird. Don't worry about it. The actual definition of temperature is related to entropy, which we haven't even covered. You'll learn that in 223. So we're not even going to talk about that. But right now, all we need to know is temperature is proportional to the average kinetic energy.
I just love how all these classes are set up, because you guys sometimes do that thing where you're like, It doesn't matter right now. You have to take
we
gears
could we
with
could
another
we could go
subject.
down a huge rabbit hole basically,
Yeah.
and we can't. We have to concentrate on this right now. So this is actually related to like IMFs and container walls and stuff. So if you drop a bouncy ball on the table, does it come all the way back to your hand? No, it kind of goes down lower and lower and lower, and that's because the collision with the ground is not completely elastic. An elastic collision means when it hits, collides with the tabletop, the energy that it had when it collided is conserved. It has the same energy when it comes back. If it did, it would go right back to your fingers, right back to your hands. When they're not elastic, that means some of the energy is lost to the container walls or the ground or something like that. In reality, nothing is completely elastic. You're always going to lose energy from friction and all that stuff. But for gases, it's safe to assume that the collisions with the container walls are elastic. So meaning we don't lose any energy to the container walls. Just for the purposes of this model, right? It's not really true, but it works if you, like this model still works to describe gases if you assume this is true. And here's a big one. So what is pressure when it comes to gases? So we have, we understand that pressure is a force applied over an area. That's the general definition of pressure. So how does a gas cause pressure? It's all of the collisions. All these tiny little molecules slamming into you or to whatever the container walls. Each little tiny collision is a little bit of force. And that force is multiplied by the number of molecules that are colliding. And there's going to be lots, because if we're talking about a mole of gas, that's a lot of particles. And so that's what causes pressure. And remembering that the collisions is what causes pressure, and the force of the collision. So if a molecule collides faster versus slow, I mean, what would hurt harder? A car hitting you at 1 mile per hour or a car hitting you at 100 miles per hour? Like, the faster it's moving, the more force it's going to have. Okay, so the faster the gas particles are moving, the higher the pressure. Which is kind of, we learn that at a macro scale. The gas laws teach us the higher the temperature, the higher the pressure. But what is happening at the atomic level? And that is collisions. The faster they're moving, the harder those collisions with the container wall. So, if you have particles going the same speed, more particles, more collisions creates more force. But if you've got particles going all of the same mass, then the faster ones are going to apply more force. So there's a lot of ways to apply more force. Right? More particles, heavier particles, or just faster particles. All right? All three of those will apply more force, will increase the pressure.
This is a stupid question. I think it is out of all the questions I've ever asked.
Okay.
Does an atom have like a front or a back? I mean, you said they go in a straight direction, and I know that makes sense with like
That-
you think of kinematics, but like they do. They don't really.
No, they don't.
So they just kind of, in their own dimensional way, just pick a direction and go with it.
Well, something had to have accelerated in that direction. Something had to accelerate them somehow. So some external force. So whether it's something else colliding with them or
just natural polarities in the environment.
I mean the initial IMFs that pulled them in one direction or something like that. Yeah,
Okay.
yeah. It's you're getting into like, so how do you measure that? Well, that's chaos theory comes in, because you can't predict everything, so you have to model it somehow. And anyway,
Yeah, that makes sense.
it's complicated.
No, that makes sense.
Yeah. Okay, so this is something we've already seen. The kinetic energy average is proportional to the temperature. And we already know from, this is a physics equation, that if you know the kinetic energy, you can calculate the speed. So this u here is velocity. Sometimes it's u, sometimes it's v. Blame physics. They use different variables sometimes. But the speed is not directly, but is proportional to the kinetic energy, which we've seen already. But this speed that we're talking about is, so it's an average speed, right? Because if you're plugging in an average kinetic energy, that speed's going to be an average speed. But we're not going to use the average the way that we normally think of an average. So our normal average is I take so let's say I have 3 different molecules, they go 3 different speeds. I will take the speed of one, add it to the speed of 2, add it to the speed of the third one, and divide by 3. That's normally how we think of average. And that is an average that is called the mean. I think it's statistics. It's the mean. But don't ask me why we use it in this particular case. But there is another kind of average. And this average is called a root mean square. And the best description I can give you for it is it's better if you've ever studied electricity, and maybe you haven't. So I'll tell you right now. Alternating current, that's what comes out of these outlets here, is voltage that goes up and down. It's a cycle. It goes 120 volts positive, or 110 positive, 110 negative. It does this. And here's the 0 line. So if I were to ask you, well, what's the average voltage? Well, positive 110 minus 110, that averages out to 0. Which doesn't make any sense. Because when you think of, well, what is the average? It's got to be something. That would, you touch it, it's going to shock you. And so this is what helps you to do averages for things that go positive, negative, positive, negative. What it does is you square all of your values first. So let's say you have 3 different speeds. You would square them first. Then you would take the average of the squared speeds. And then the result you would take the square root of. And what the squaring does is it gets rid of the negatives, makes the negatives positive, right? Square a negative makes it positive. Yeah. So that's how it helps in AC, stuff like this. I am not positive how it helps here, but this is another average that is very common to see. So RMS is root mean square. So if you see it, how do you think of it? Well, even though it's not the same as our regular average, it's proportional to an average. So just go with it, all right? But I'm just giving you the definition so you know what it is. And this is the average when we talk about an average speed, all right, as that root mean square speed. So here's our Boltzmann distributions. We've seen this before. We have here 2 different curves. These are 2 different containers of gas, one at a low temperature, another one at a high temperature. Remember, the average is not where the peak is. The average is just to the right because these are not symmetrical peak or curves. They kind of taper off here this way. And so how would you describe? Well, as you increase the temperature, the average speed increases, and the peaks broaden out. So at low temperature, the peak is pretty sharp. At higher temperatures, the peaks broaden out. Now, we focused on Boltzmann distributions with kinetic energy as its x-axis. We are going to now look at Boltzmann distributions with speed on the x-axis. And, that makes it a little bit more complicated. I think on the homework, or we did an activity, what are the Boltzmann distributions for these 2 different gases or 3 different gases, but if they're at the same temperature? Well, you would draw the same distribution. But when it's speed here, and that's because kinetic energy is proportional to temperature. That's it. There's nothing else. But when it's speed, you have to worry about the identity of the gas. Okay. So with temperature, it's the same. Here's low temperature. Here's high temperature. The average is higher now, and the curve is broadened out. So the peak, again, is the most probable speed, but the average is a little bit to the right. So how do we calculate that average now? So this is something we just kind of hand-waved before. Well, we can calculate that root mean square speed, that average speed. And notice that it's dependent on 2 variables. The temperature, which makes sense because the temperature changes that distribution, but also the molar mass. So how heavy the gas is will affect what its average speed is going to be. And I mean, so take a look. The higher the temperature, that's in the numerator. If the higher this temperature, the bigger the numerator is going to be, the bigger the speed is going to be. Makes sense? But the larger the mass, the bigger the molecule, heavier the molecule, the denominator will get bigger. That will make the speed slower. Which should make sense. That the heavier something is, it takes a lot more energy to move something heavier than something very light. So heavier atoms are going to go slower on average. And there we go. So, oh no, this is not two different atoms. This is looking at temperature. So here I've got nitrogen at 0 degrees and nitrogen at 100 degrees. And obviously, if I increase the temperature, the root mean square speed increases. It goes from that blue dotted line to the yellow, or red dotted line. Dashed line, I guess. Now, there's a couple hiccups you need to be aware of when you use this equation. Temperature is in Kelvin. R is going to be the gas constant that has energy in it, because there's no liters, there's no atmospheres. We don't need those. We need energy. But I'm going to warn you, you guys remember what the energy derived unit actually is made up of. So remember, for SI units, there's only like 6 fundamental SI units. Kilograms, meters, seconds, moles, and then a couple physics ones that we don't care about. Everything else is a derived unit, meaning it's made up of those fundamental units. A joule is a kilogram meters squared per second squared. That's what a joule is. Yeah,
That's what it is.
that's what it is. So if your R has joules per mole, Kelvin per mole, then when I break this apart, it's going to be kilograms meters squared over Kelvin moles second squared. All right, that's what the R units are going to be. Now, you can see that when I multiply by a temperature, that's going to cancel out my Kelvin. But what about the molar mass? Notice that it has kilograms in it. Our molar masses generally are grams per mole. So when you use this equation, your molar mass, you have to convert it to kilograms per mole. So for nitrogen, nitrogen has a molar mass, it's N2, of 28 grams per mole. So instead, you would plug in, not 28, you would plug in 0.028 kilograms per mole. That way the units cancel out. You'll get rid of the kilograms here, you get rid of the moles here, and you'll be left with meters squared per second squared, which are taken care of by the square root. The square root gets rid of the squareds, and you're left with meters per second, which is exactly what speed is. So be careful. Your molar mass must be in kilograms per mole to use this equation properly. So here's the graph that shows, all right, now we're not changing the temperature, we're changing the identity of the gas. So all of these gases have different molar masses. And you can see that oxygen's the heaviest gas there, 32 grams per mole. It's moving the slowest on average. Whereas hydrogen is the lightest one, 2 grams per mole. The peak is very broadened out. And here is the most probable somewhere here. The average is somewhere to the right, somewhere over here. The average speed is much higher than the rest of them. So the lighter the gas, the higher the speed, if they're all the same temperature. Okay. Now, if they're different temperature, different molar mass, you'll have to calculate what the average is. But you can then, now you can see how they work. Okay. So, let's see if I can get you guys to agree on these things. If I have a large container, big one, and a tiny one, and they both contain the same number of moles at the same temperature, then would the kinetic energy be different between them, or would they be the same? So big container and a small container, same number of moles, same temperature. The kinetic energy between them is the same or different.
Oh, we need a biggie?
Yeah, that'd be nice.
Does it matter which box of these we use?
Oh, the one that goes 1 through whatever, if it's there.
Quick
Sorry, I
question.
forgot to pull those out. I'm sorry. Stupid fire alarm. By the way, did anybody walk off by accident with one of those on Monday? If you did, no big deal, but like some people can require a specific one. All right.
It's not actually. It's literally just tape. Actually.
Oh, okay, never mind that.
They're completely useless outside.
I know.
Scared of him.
But other classes, like I don't care for you guys, but other classes they assign a number and they look at who's been voting and the student needs that number. So if somebody walks off with it, they're like, oh, where's my limit? Yeah.
Are we doing just the first one?
Yeah, just the first one. Kinetic energy, same or different?
Are we just doing practice questions?
On Monday.
Gas. We're on gas right now for the class.
Yeah.
I'm gonna try to beat traffic because if
Oh,
I don't leave
that-
now, if I don't
that-
leave now, I'm on the highway for an hour.
We're gonna do the real gas equation after this too.
Okay, I'll wait.
Okay. Oh, we don't have much time, do we? Okay, we're gonna hurry through it. All right. So, So, what's the answer? Come on.
It would be the same.
It would be the same. Why?
I
Kinetic
don't-
energy is dependent on temperature only. So kinetic energy is proportional to temperature, and that's it. So if they're the same temperature, they're going to have the same kinetic energy. Now, velocity distribution, same or different?
It has to be different. Because aren't they bumping into each other like crazy in the small?
Well, vote. Let's see what you think.
Then
Let's see what people think. Oh, everybody voted already. Okay. So, oh my God. So it's the same.
Oh, wow.
So why is it the same? Because it's the same gas. If it was a different gas, if they had different molar masses, then they'd be different. So if it's the same gas, it doesn't matter that there's more gas. It's the same gas, same temperature, same velocity distribution.
The only thing that changes with a container is pressure.
So what'll change the velocity is a different temperature or a different molar mass. Yes?
So, I mean, the square root stuff, are you gonna, like, what kind of questions of that should we expect on the exam?
What's the root mean square speed of oxygen at 300 Kelvin? Something like that. Is that clear? I mean, so if you need to calculate, there's one, or I could give you a Boltzmann distribution with a couple different gases, and I'll label all the RMS speeds, and I could say what's the molar mass of this particular gas.
Right, and so we're just gonna have, like, use the equation to find M.
Mm-hmm.
Okay, fine.
It's not too bad, right? Okay. But these questions are work too. These, like, kind of understanding conceptually what's going to change, what's going to be different. So I like these two. Okay. So now I've got different scenario. A large container and a small container, same number. No, it's the same scenario. Same number. The frequency with which collisions occur, is it the same or different? So large container, small container, same number of moles of gas in each one, same temperature. All right, let's see. Excellent. So why is it different? Well, if they're going the same average speed, a smaller container means they're going to hit the walls more often. I mean, we can even apply regular gas laws to it. It's the V is smaller, the P is going to go up. Why P? Well, frequency of collisions. That's directly proportional to the pressure. The more collisions you have, the higher the pressure is going to be. And so I just gave that away. The pressure is going to be the different. Okay? All right. So there's a visual of like that scenario. Same gas, same number of moles, one's in a smaller container. All right. What about this? I've got a container of gas. It's heated. The average velocity is what? Greater, smaller, the same than it was before? Okay. Everybody got that right? Yes, it is greater. What about the kinetic energy? Okay.
Oh, wait.
Oh, I already canceled. It's okay. All right, excellent. Kinetic energy is now greater. What about the force per collision? Okay, well, most of you got it. So force, the collision's force. So there's three things that affect how hard, well, there's two things that affect how hard it hits. One is the speed that are going, and two is the mass. The higher the mass, the harder it'll hit, right? You don't want to be hit by a car. I mean, a pebble going 50 miles an hour versus a car going 50 miles an hour, I want to be hit by the pebble if I have to choose. It's going to still sting, but it's better. What about the frequency of collisions? There we go. So the frequency of collisions is still greater. So why more collisions? Well, they're moving faster. So the faster they move, the more likely they can get from one side of the container to the other faster. And then I'm not going to turn this one on, but the pressure is now greater. Okay, so you should be able to both use the bulk laws, like the gas laws, using PV is P1 V1 is P2 V2, to talk about pressure changes, volume changes. But you should also be able to think about it at a molecular level. What is happening to cause these pressure changes? Right? Pressure changes are caused by increased collisions, or increase in pressure causes by increased collisions. And not only increased number of collisions, but increased force of the collisions. So think about what is causing that. Is it a heavier molecule? Is it a faster moving molecule? Is the greater number of collisions caused by more molecules? Or is the greater number of collisions caused by a smaller container, meaning it has to travel not as far? So all of these will kind of affect what is happening in the macro scale, in our, how we measure pressure and volume. So I got two curves, A and B, and these are velocity distributions. We have velocity on the x-axis. Which one represents hydrogen gas? So hydrogen versus methane. It'll make sense in a second if you're not sure. There we go. It is B, yeah. So why B?
Hydrogen's lighter.
Lighter. Molar mass is lower. Lighter gas. It, again, comes back to this.
Wait, what is velocity?
Is it also with the...
Velocity speed. How
Can I
fast
do
they're going.
that? Okay, yeah.
Is, I don't know if this is like the same or correlated. I guess it is correlated, but like even if the mass is bigger, like it's saying the number of particles in CH4 has 5. Right?
Well, so CH4 has 5 atoms, but it's one particle because it makes one molecule. So, but what matters here is, doesn't matter how many particles there are. This is a velocity distribution. So how is the velocity affected? Temperature or molar mass, and that's it. And they're going they're the same temperature. So all we can rely on is the molar mass. And hydrogen's lighter, so it's going to have a higher velocity because of that. Okay. And you'll get that equation too, don't worry. Which one has the higher temperature if they're identical gases? All right. Hopefully that one's easy. Hopefully. going the wrong. Well, okay. It is B. So again, higher temperature generally means higher kinetic energy. Higher kinetic energy means greater speeds, especially if they're the same types of molecules, okay? Because then we don't have to worry about the mass. Yeah, A and B are identical gases, yes. Yeah. So it's okay, you'll have more time on the exams to read these and think about it some more. This is quick, which is fine, but hopefully it challenges your automatic assumptions. So this is just a nice little chart that shows kind of everything we've covered.
Is that on detail?
Well, this slide is, yeah. If you go to, there's a link for lecture slides. So yeah, we've got ideal gas law, we've got molar volume, and we've got and then the STP things. We've got Dalton's law, we've got kinetic molecular theory. So this is a nice little flow chart to kind of verify that you know what you're, you know all the sections of this
That's beautiful.
here. I guess what's not on here, I mean, we could expand this out and talk about that equation that shows root mean square speed and stuff too, but it's there. Okay, so last thing. Yeah, I'm going to skip this real quick. I want to get to real gases. So we've covered this. So hopefully, these are when to use each case. Here we go. So far, we've been dealing with ideal gases, and the ideal gas follow all the assumptions of the kinetic molecular theory. Specifically, though, no intermolecular forces and no volume. So what happens when you're at super cold temperatures? So if something is super, super cold, how fast is it moving? Pretty slowly. And if gases are moving really slowly and they get near each other, maybe the IMFs will start to play a role. It'll start to be attracted to each other. And just to give you an idea of how all IMFs affect pressure, if I've got a particle that's heading for the container walls, right? When they collide with the container walls, that's what provides pressure, right? Every collision adds to the pressure. Well, let's say there's another particle right here, and it's going this way. What do you think might happen to the path of this particle if it gets near this one and it's attracted? It's going to veer. It's going to kind of, like, once this gets close enough, then this thing is going to not go straight. It's going to veer that way because it's going to be slightly attracted, right? It's going to change its path. And so if it's not heading to the wall anymore, look, it's taking a longer route to get to the container walls. So anything that will impede these collisions is going to lower the pressure. So IMFs, when they start to matter, are going to change the pressure. Let's talk about, so that's the low temperature case. What about when I do super high pressures? What's happening to a gas when I go super high pressures? So how do I get super high pressures? I could reduce the volume to really tiny volumes. But what is happening to the gas particles when I shrink the volume? Are they getting... They're getting compressed. They're getting closer together. And that means they're more likely for the IMFs to play a role. Also, if I'm taking away all the empty space, what about that assumption that the gas particles themselves take up no room? Well, now the space they take up is going to start becoming important, but it's taken up. So when I get to super high pressures, then my ideal gas equation is also going to fall apart, because the volume that the gas particles take up is going to matter now. So we've got this equation here that corrects for all that, okay? So I want you to notice that this thing is still pretty much P. This thing is still pretty much V is equal to nRT. It's still based on the ideal gas law, but we've got some corrections. So this thing right here corrects for the amount of space that the gas actually takes up. So, I've put my gas in a 2-liter container. Normally, I'd plug in 2 liters for volume, and that's it, or for this thing. But now, I'm going to subtract the space that the gas takes up, so that I'll have a little bit of less container space. So this N is the number of moles. This B is a constant, and it's very specific to the gas you use. So oxygen has its own B, nitrogen has a different B. This is something you have to look up. You don't memorize this. And then over here, this is a correction for intermolecular forces. So the idea here is that A is a constant that kind of talks, that describes in general how the intermolecular forces will affect the gas. And so it's A times the number of moles divided by volume squared. So imagine if I were to ask you to solve for N in this thing. I've got an N here, I've got an N here. How would you solve for it? It'd be very difficult. So you're not going to have to do that. Don't worry. The only thing you would have to solve here is for P. And I don't know if the next slide shows that. Let me see. No, it doesn't. So I can rearrange this equation to solve for P. And it's not too hard. So I'm going to move this over here. So I'm going to divide both sides by V over minus NB, and that's going to go down here. And then I'm going to subtract both sides by this. So what ends up happening is your pressure is equal to V minus NB over, no, sorry, wrong way. Pressure is equal to nRT over V minus NB minus A times N over V squared. This is the the van der Waals equation, which is the real gas equation. And again, A and B are constants you would look up. All right, they should be given to you. You don't have to memorize anything. So you can calculate P. It's just tedious. Make sure you don't make any mistakes. Do this part first. Do this part separate. Have those numbers handy, and then put it all together. It's very easy to do order of operations mistakes. So try it. Make sure your answers match what the book or the Mastering Chemistry answers are. Yeah.
So there's N in like 3 different places.
It's the same N. It's the number of moles of your gas.
Right.
So like I said, I'm not going to ask you to solve for N. That's not possible with our class. Even I would have trouble solving for N. The only thing we would ask you to do for this equation is what is the pressure. So what is here's a very important question. I could ask you, what is the pressure of a gas using the ideal gas law, and what is the pressure of the gas using the van der Waals equation? And you'd actually get slightly different answers, depending on what the conditions were. So when do you use this? When is this important? For conditions like we're existing at now, you would never use this. The ideal gas law, PV equals nRT, is perfectly fine. It gives you a very accurate answer. But if you're at super low temperatures, or conversely, at super high pressures, and what is super high, what does super low mean? It's relative. You're going to have to, the problem usually will tell you. It comes from experience, though. They'll tell you to use this equation if you need it. So under those extreme conditions, the answer for P for the ideal gas law and this equation are going to be very different. And this one's going to be the more accurate one. Okay? So here is kind of a graph that shows you the deviation from ideal gas law. So what do I mean by that? So if I have pressure versus the molar volume. So you can rearrange PV equals nRT to get molar volume. The volume of 1 mole of a gas. And at low pressures, around 1 to 100, the ideal gas and the real gas equation match up pretty well. They don't split. But they start separating when you get to really high pressures. So you get 2 different answers, whether you use the ideal gas equation or the real gas equation. Yeah?
So when you give us problems calculate the pressure for the real gas versus the ideal gas, are you going to give us a higher pressure so we get slightly different answers?
Well, I wouldn't give you the pressure. I would give you a number of moles, I'd give you a volume, and I'd give you a temperature.
Yeah, so would you give us super low temperatures?
Probably, yeah. Yeah. And so, well, the interesting problem is you get different answers. If I give you a regular temperature and a regular volume and a regular number of moles, your pressures will end up being the same. Yeah. So here's a note. So this is the extreme pressure case. You can see that there is a difference. And then here is the extreme low temperature case. So when you get to, and this is not even that low. This is, look, room temperature is right around here, somewhere right here. There is already a difference between the ideal gas of xenon versus the real gas equation for xenon. But the lower the temperature, the more extreme it becomes, the more different it becomes. Okay. So here are some constants, and these are in your book. These will be provided in problems when you need them. Like I said, A is somewhat related to the intermolecular forces, and so it should be no surprise that something like water has a pretty large A, whereas something like helium has a pretty small A, small IMFs. And B is related, and this is less obvious, but B is related to the size, how much space it takes up. It's not as obvious. This one's less, it's harder to tell any trend here. But again, don't memorize any of these. You'll be provided them if you need them. Here's another graph that shows you what happens between real gases and ideal gases. So what we're doing here is putting, if I have 1 mole of a gas, all right, let's say I have 1 mole of a gas, and I rearrange PV equals nRT to solve for n. Well, if it's an ideal gas, whatever the pressure, whatever the volume, whatever the temperature is, I should get 1 mole every time. And that's what this pink line says. No matter what the pressure is, even if it's super high, if it's an ideal gas, like if it's truly an ideal gas, and nothing is really an ideal gas, but if it really is, you should get 1 every time. But if it's not an ideal gas, and that's every case for real, you won't get 1. So here, when you start increasing the pressure to super high pressures, you get really big deviations in the ideal gas law. So here, CO2 starts off going lower than what you'd expect, and then it goes higher than what you'd expect. So why is that? Well, when it goes lower than this, the attractions, the intermolecular forces dominate. The attractions basically lower the pressure. But then suddenly you get to really high pressures, and now the volume of the gas, like the space that the molecules take up, start to predominate. And you run out of room for these molecules. And so the pressure starts skyrocketing higher than you normally expect. So here, this one is methane. Initially, the intermolecular forces, the attractions dominate. But then eventually, the space, like the molecules take up, start to dominate, and the pressure skyrockets. Here, hydrogen and helium, which already had really weak IMFs, like they're hard, they're not very polarizable, they're nonpolar. They hardly have any IMFs at all, so really it's just the space that they take up dominates. So that's all we're showing you here. So just at extreme cases, intermolecular forces and the space that the molecules take up play a big role. All right, I want to skip this one because I don't like that question. But that's it. That's all I wanted to show you. I think in the case of the ideal gas or the real gas equation, all you'll have to do is learn how to plug things in. That's it. We're not going to do any crazy problems. So it's just a plug and chug problem. You'll get a homework problem with that. Please try the homework for next week, like ahead of time, because I believe that this week's homework.
Just do on Monday.
You guys have a homework due on Monday, but I think that the following homework is also gas law stuff. I'll have to double check, and that's due after the exam, but it'd be worth it to try it before the exam. So.
I have the same question. I remember asking Monday,
Yes.
like, remember what
But when you implement t, there's already t squared. That becomes delta x because do you know what I mean? But do you know what I mean? Though? It's all like, how was I supposed to know that?
So the size that controls the bond length.
Professor,
Yeah.
just to confirm, we do have lab next week, don't we?
Yes, we do.
Which lab?
6, I think.
This is the
Okay.
method my tutors use in my private way.
I'll make sure real quick because I.
And we have the exam after?
Basically, it has everything from
Yes, yes, we're Wednesday, right? Yeah.
and it's just videos, and you just sit there and
Alright.
breaks it down like one time. It's a 45-minute lesson.
Thank you.
But
Yeah,
it breaks
yeah,
it
see ya.
down, like, it breaks basically like,
Oh, that's the wrong one.
It's literally the notes that are on the thing.
Yeah, it's.
I'll have to bring you the link.
I feel like I need an in-person class for that one.
Yeah, it's just one of those things where you might have to get a tutor. To
Yeah,
like,
6. Okay, that's it. Oh yeah, this is gonna be early. That's fine. This
Yeah,
will.
I spent like over 30 minutes doing a math problem. I can't remember what the math problem is right now off the top of my head. It's a kinematic equation. And so I'm sitting here and I'm trying to do this long one, and I have like x, and then I have like xt, and then I have something else like 1/2 a, and then t squared. And I had something over here, right? And so for like the longest time, I even had the answer key, because they give us the answer keys. And I couldn't figure out where this t went. It disappeared because for some reason when you remove the x over here and put it over here, it becomes delta x, because I'm supposed to know that that means the difference in time. And I swear to you, that's when I got mad at math for this week. Because I'm sitting here, I've never in my life.
I haven't seen that before.
Never in my life have I seen math turn into Greek in the middle of a math problem. Like, that was BS.
So on Tuesdays, I've been going to the tutor center. There's this woman, Irene, who
Yeah.
does all the math.
Oh yeah.
And so I just hang out for like, I mean, now
That's what I need to do.
a couple hours, yeah, on Tuesdays.
I have a private, there's a website that I really love, and it's called it's literally called the mathandsciencetutor.com.
Oh,
This dude's been doing it since like the late 80s, and so he has his videos on there, and you pay $20 a month, and he has, at this point, he has an entire archive of every single subject that's ever existed. So you can sit there and be like, I need to learn, gas law, and he'll do like a 45-minute gas law like video, and it's just on gas law, and so I'll probably go